In section 3, we are going to look at the angle between two non-parallel lines. Now, the angle between two non-parallel lines, by convention, is the acute angle theta between them. So, in this particular diagram, we have the line L1 with direction vector D1 and the line L2 with direction D2. The acute angle between the two lines, defined by theta, can be found by finding the angle between the acute angle between the direction vectors of the respective two lines. Consider the two non-parallel lines L1 and L2. L1 has this vector equation and L2 has this vector equation with their respective direction vectors as D1 and D2 respectively. Now, if we let alpha to be the angle between the direction vectors of the two lines, by using the definition of the scalar product that we have seen before in vectors 1, the dot product between the two direction vectors is defined as this. D1 dot D2 is equals to the magnitude of D1 times the magnitude of D2 times the cosine of the angle between the two direction vectors. Now, if alpha is equals to theta, where theta is acute, we will then have the version of this formula seen in this form. The reason we put a modulus on the left hand side is because when theta is acute, the cosine of the angle theta is a positive value, and therefore we need to ensure that the left hand side will also be a positive number. So therefore we put in the modulus. So from here we can actually make cosine theta the subject, and we will actually obtain cosine theta equals to this portion divided by this portion. So based on this, we can get the formula for the acute angle for any pair of non-parallel lines, whether they are intersecting or skew, given by this formula. In example 10, we are asked to find the angle between the line AB and the y-axis, giving the answer correct to the nearest 0.1 degrees. Now, the line AB is formed by joining the 2 points A and B, of which having coordinates 2, 3, -1 and 5, -2, -3 respectively. So from this simple diagram, the line contains the 2 points A and B, and the direction vector of the line can be found by finding the vector AB as shown over here. Now, the direction vector of the y-axis is the unit vector j, which is parallel to the y-axis and has a column vector which is 0, 1, 0. So in order for us to find the angle between the line AB and the y-axis, we use the definition of the dot product as shown over here. So we take AB dot with the unit vector j. The unit vector j is parallel to the y-axis. So by definition, this will be equals to the magnitude of AB times the magnitude of j times the cosine of the angle between them. And in order for us to get the acute angle, we put a modulus on the left hand side to ensure that the left hand side is a positive value. So from this formula, we can make cosine theta the subject, and eventually we can get the formula for theta itself. and from here we can start to put in the values to evaluate what is the actual angle between the line AB and the y-axis. Now in section 4 we are going to look at how to find the foot of the perpendicular from a point to a line. So on this particular diagram we have the line L which contains the point A having the position vector A, and we have the point P which is not on L. The foot of the perpendicular, the point F, is situated on the line L such that PF is perpendicular to the line L. Now there are two methods to find the foot of the perpendicular. The preferred method is method number 1. Now in method number 1, first of all, since F lies on the line L, the position vector of the point F can take the equation of the line L for some value of lambda. We then go ahead to find the vector PF, which will be in terms of lambda. The concept that is applied in step 3 is that since PF is perpendicular to the line L, the dot product between the vector PF and the direction vector of the line L will be 0. From there, we will be able to solve for the unknown lambda. Using the found value of lambda, we can therefore put back the value of lambda into the equation over here to get the position vector of the point F, the foot of the perpendicular. Now depending on the question, we may need to give the point F either in terms of its coordinates or in terms of the position vector with respect to the origin. So we need to read the question carefully on what is required for the particular question that we are doing. Now in method number 2, if we are familiar with the projection vector as we have covered in vectors 1, method number 2 may be suitable. Now in step 1, we find the projection vector AF. Now the vector AF, as seen in the diagram, is the vector formed by joining the points A to F. Now the vector AF is actually the projection vector of the vector AP onto the line L. From vectors 1, this projection vector has this formula. After we have found the projection vector AF, we can actually find the vector OF using the relationship over here that we are familiar with. Now upon finding the position vector of the point F, that is OF, we will also be able to find the perpendicular or shortest distance from the point P to the line L, which is the line segment PF itself. In other instances, we would also be able to find the position vector of the reflection of P in L So based on this diagram, the reflection of the point P about the line L is the point P prime. Since P prime is the reflection of P about the line L, the distance here and here are equal, and therefore we can use the midpoint theorem and thus get the position vector of the point P prime by making this vector the subject. In example 11, we are given the line L with this equation and a point P which is not on L with this position vector. we are asked to find the position vector of the point F, which is the foot of the perpendicular from the point P to the line L. So for vectors diagram, it is advisable for all of us to actually draw a simple diagram. So based on this paragraph, we have the line L, which passes through the point A with these coordinates. The point A is actually obtained from here, and the point P, given the position vector of 0, 1, 5, will have these coordinates. The point F, being the foot of the perpendicular, is such that the line PF will be perpendicular to the line L. So how do we find the position vector of this particular point? We shall look at the two methods that we have covered in the previous section. So method number 1, we use the fact that the vector PF is actually perpendicular to the line L. So if vector PF is perpendicular to the line L, it is also perpendicular to the direction vector of the line. The direction vector of the line, according to the vector equation, is actually 1, 0, 2. So since F lies on the line L, the position vector of the point F is still unknown, but we can actually write the position vector in terms of lambda using the vector equation of L itself. So OF is given by this column vector for some values of lambda. If we are able to find the value of lambda, then we have found the position vector of F. Now, using the fact that PF is perpendicular to the direction vector of the line L, we go ahead to find what is PF in terms of lambda. Since PF is perpendicular to L, so therefore it is perpendicular to the direction vector of the line, which is in this case the vector D, given by the column vector 1, 0, 2. And the result of this dot product between PF and the direction vector of the line D is equals to 0. Evaluating the left hand side, we will be able to get an equation where we can solve for lambda. So in this case, lambda is equals to 1. Since now we have discovered what is lambda, we can use this value and put it into the equation over here to find out what is the position vector of the point F. In method number 2, we use the projection vector concept. Now in this diagram, AP is the vector joining the point A to P, and AF is the projection vector of the vector AP onto the line L. So our first objective is to find what is the vector AF. Now using the formula that we have discussed earlier, the vector AF is given by this formula. Right, so in order for us to use this formula, we therefore need to find what is the vector AP. The vector AP can be easily be found using this relationship, and then now we are left to evaluating what is this formula. So based on what we have found, AP is this column vector, and the unit vector D over here is actually the unit vector for this direction vector. Right, so to complete the expression, we substitute in all the necessary details. So AP, the vector, is given by negative 3, 2, 4 column vector. The unit vector D is basically the vector 1, 0, 2 divided by the magnitude. With that, we can evaluate what is the vector AF. So based on this, this dot with this will give us this component. root 5 times root 5 will give us this component, and therefore we are left with this component over here, right? So the vector AF will now be reduced to the column vector 1 0 2. From there we can therefore find the position vector of F according to this relationship. Now in section 5 we are going to look at how to find the perpendicular distance from a point to a line. Now suppose F is the foot of the perpendicular from a point P to the line L. So on this diagram the point P is not on L. So if we were to drop a perpendicular, F is the foot of the perpendicular, and the line segment PF is as shown. So to find PF, we consider the equation of the line L, usually given in this form. So there are quite a number of methods for us to actually find the shortest distance or the perpendicular distance from the point P to the line L. Alright. So method number 1, which is the fastest, is using the vector cross product formula, alright, which we saw in vectors 1. And the formula is to find this distance PF, we find the modulus of the vector AP cross with the unit vector of the direction vector of the line itself, right? So this is a formula based on vectors 1. Now this method is the simplest method and the fastest method to get the shortest distance from the point P to the line directly. Now in method number 2, we use the foot of the perpendicular as discussed in the previous section. Now this method is suitable when the foot of the perpendicular F was found earlier in the question. So the method is actually quite straightforward. In method number 3, we use a scalar product and Pythagoras theorem, right? So in method number 3, we actually go ahead to find out what is the length of projection of the vector AP onto the line L, so this part, right? So once we have found this length, using the length of projection formula that we have discussed in vectors 1, according to this, we can actually use Pythagoras theorem to find the length PF. Now this method is suitable when the length of projection of AP onto the line L, which is the line AF itself, was found earlier in the question. Now in the last method, method number 4, we use this method when the cosine theta, that is the angle between the vector AP and the line L, has been found earlier in the question. Right, so to find the cosine of the angle theta over here, we use the definition of the dot product as covered before, and once we have found that, we can actually use sine theta in the right angle triangle over here to find the length PF. Alright, so basically PF is equals to AP sine of this angle, right? The line segment AP is basically the magnitude of the vector AP itself. Alright, in example 12, we are supposed to find the position vector of the foot of the perpendicular, the point F, from the origin O to the particular line L given by this equation. After that, we are supposed to use a hands approach to find the shortest distance from the point O to the line L. So using a simple diagram, we have the line L, which contains the point, we label it as A with these coordinates. So this point is actually obtained from this part of the equation. And then this line L has a direction vector, we label it as D. This direction vector is obtained from this part of the equation. Alright, so the two objectives of this question is number 1, to find the point F. So to find the point F, in this particular question, they ask for a position vector. So we're going to look for OF. Then next, using the hands approach, we're supposed to find the length of the distance over here from O to F. Alright, which is basically the magnitude of the vector OF itself. Alright. So using the method number 2, since the point F lies on the line L, the position vector of F can be obtained from the equation itself, right, for some values of lambda. Okay, so position vector of F can be written as so. Alright, in terms of lambda, for some values of lambda, alright, we can write down the position vector of F. And then based on the diagram, we know that OF, the vector OF, is actually perpendicular to the line L. Alright, so since it is perpendicular, that means OF is also perpendicular to the direction vector of the line L. So by using this fact, we can actually make use of the dot product. Since they are perpendicular, the vector OF and the direction vector of the line, when we do the dot product, we should get the zero scalar. Alright, since we have written the position vector of F in terms of lambda, we can replace it inside here, and then from here we can actually evaluate the left hand side and solve for lambda. Alright, so for lambda equals to -1, it will actually describe this exact point when lambda is equals to -1, such that OF is perpendicular to the line L. Okay, because it satisfies this equation. So by substituting lambda equals to -1 into this expression over here, we will be able to get the position vector of F. So once we have found that, because this vector itself is OF, and this happens to be the shortest distance from the origin to the line, basically what we need to do is to find the magnitude of this vector, which is square root 6 in this case. In example 13, we are given a point not on the line L. The point has position vector 1, 2, 3. The line L has an equation as shown over here. We are supposed to find the length of the perpendicular from the point P to the line L. Alright, so using a simple diagram again, the point P will have coordinates 1, 2, 3 because the position vector was given as 1, 2, 3, column vector 1, 2, 3. The line L has equation. This part here will give us a point on the line. So we will label this point as 1, 4, 1 with coordinates 1, 4, 1, and that comes from here. The direction vector of the line is obtained from here, and we label it as D. Alright. So in this particular question, we're supposed to find the length of the perpendicular from this point to the line. So it's basically the line segment PF. Okay. So in this solution, we are going to use method number 3. Now method number 3 is using Pythagoras theorem, right? So if we were to look at this particular setup, alright, this we realize is a right angle triangle, and because this method uses the Pythagoras theorem, therefore we are going to look at the hypotenuse squared equals to this side squared plus this side squared, and this side squared will actually give us the length of PF squared, right? So some of the things that we need to evaluate will be the vector AP, and then finding the vector AP will give us the magnitude of AP by using the simple formula. Alright, now in order for us to use the Pythagoras theorem, because this is a hypotenuse, alright, so hypotenuse squared minus AF squared will give the PF squared. So therefore we need to find what is AF. So based on our vectors 1, the distance here from this point to this point, the AF, the line segment AF, is basically the length of projection of the vector AP onto the line. Alright, so this AF here is actually the length of projection of the vector AP onto the line L. And if you could remember, in vectors 1 we have covered the specific formula already. Alright, so the formula is basically shown over here. Okay, so the formula says the length AF, which is the length of projection of the vector AP onto the line L is basically the vector AP dot with the unit vector parallel to the line. So this is the direction vector of the line, so the unit vector will be parallel to the line itself. Okay, so the unit vector is basically if this is the unit vector, the formula for the unit vector D will be just the vector D divided by its magnitude. Alright, so this direction vector is still not in the unit vector form, so we take this vector divided by the magnitude will give us the unit vector parallel to this line L. Okay, so now we can start to put in the details. Okay, so AP we found it to be 0, -2, 2, so this is the column vector for AP. 1 over root D will be 1 over square root 3. Alright, because square root 1 square plus 1 square plus 1 square is square root 3. Alright, and vector D is this vector itself. Alright, so to after evaluating, we will get the distance AF as 4 over root 3. So now we are left to find PF itself by using Pythagoras theorem. Okay, so using Pythagoras theorem, basically PF is just the square root of AP squared minus AF squared. Alright, so since we already found out what is AP based on the earlier result here, and we just found out what is AF, okay, based on this one, we can get the length PF by Pythagoras theorem. Now in example 14, there are 3 components that we are supposed to find. Alright, so let's look at the question. It gives us the line L with the vector equation given as this. Now the moment you look at the vector equation given as this, right, there is no point component in the vector equation, so that means the origin actually lies on the given line over here, because this equation can be written as R equals to the 0 vector plus T 1, 2, 3. Alright, this is the 0 vector. So based on the format of this vector equation, alright, we can therefore say that the origin is actually on the line. Okay, so further details that they give us is that the point P has coordinates 3, 4, 1. So we're supposed to find the foot of the perpendicular from P to this line, and then using the hands approach, find the perpendicular distance from P to this line. Then the third and final goal of the question is to find the position vector of the image of P in the line L. Okay, so let's draw a simple diagram. So the simple diagram is this. We have confirmed that the origin lies on the line L, so we place the origin there. P is obviously a point not on L. Alright, so to find the foot of the perpendicular, we let F to be the foot of the perpendicular, so that means this particular triangle is a right angle triangle. So this one is confirmed to be a 90 degrees angle. Okay, alright. So once we have labeled this one as F, alright, so later we're supposed to find what is the position vector of F, which is OF. Alright. Then next, once we have found what is the position vector of F, we can actually get the vector PF. Alright, and then find the magnitude, and that will give us the perpendicular distance from P to L. That is a hands approach, because once we have found the foot of the perpendicular by finding the vector PF, right, finding the vector PF, okay, and then after that finding the magnitude of this vector, alright, we will be able to find this distance here as required over here. Okay, then questions also say in the last part is to find the position vector of the image of P in the line. So what do we mean by image of P? So this is a point P, right? The image of P is a reflection of the point P about this line. Alright, so the reflection of this is actually this point, we call it P prime. Alright, when that is the case, right, that means this P prime is also when we drop a perpendicular to the line L, alright, it should also reach the point F. Okay, so that means this length and this length are both equal. Okay, Alright, so first and foremost, we need to find what is the position vector of f, and based on the previous example, since f actually lies on this line, right, the position vector of f, alright, can be taken from the equation of the line L. Okay, so we have this. Alright, so since f lies on L, the position vector of f can take the equation of the line L, okay, for some values of t. Alright, so next we just want to find what is a PF, okay, the vector PF. Using the fact that PF is perpendicular to the direction of the line L, alright, we should do a dot product, and then from there we should be able to get the value of t. Okay, so the next step, once we have found PF as this, okay, so we're going to take PF, alright, since PF is perpendicular to L, the dot product of PF with the direction vector of L should give us 0 because perpendicular. Yeah, so this is a concept that we are applying, and because PF is in terms of t in the previous page, alright, so we are left to evaluate this dot product. Okay, by now you should be able to evaluate this dot product easily. Okay, so solving for t, we actually get t equals to 1. Alright, so from t equals to 1, we can find the position vector of f by taking the value of t equals to 1, putting it not into here, alright, because this is PF, so we should actually put the value of t, alright, value of t found here into the coordinates of the point f, which was earlier on in terms of t. Alright, so when we do that, we actually get the coordinates of f. Okay, so once we have found the coordinates of f, that is the first goal of the question. The second part of the question, they ask us to find the distance here. Okay, and using the hands approach, so that means we actually need to find the distance by finding PF first. So PF, now we can take the value of t equals to 1, right, put inside here, because this is PF, the vector. Okay, so once we do that, we have this vector. So to get the magnitude of PF is basically the magnitude of this column vector. Alright, so that will give us this length. Now in the last part, the image of P, as we have shown before, is P prime. Alright, so how do we actually obtain P prime? Here is where we actually apply the ratio theorem. Because we know the point F already, we know this point P, so we can use the ratio theorem. In this case, the ratio is 1:1. Alright, so from here, so by using the ratio theorem, alright, the OF can be written as OF can be written as OP plus OP prime divided by 2. The ratio is 1:1, so you have 2 over here. Alright, and then from there you can actually make OP prime the subject. Alright, and that's where you get the position vector of the point P prime. Now example 15 is the last example, so let's take a look at it. Alright, so relative to the origin O, the position vector of the points A and B are given as the vector A and B respectively. So we can draw a simple diagram. Alright, so this is the origin. Now we read a little bit further. Given that the angle AOB is 90 degrees, so this angle is 90 degrees, so this vector is A, origin, this vector is B. Alright, so vector A represent the vector describing the point A, vector B represent the vector describing the vector B describe the vector representing the point B. Right, so find in terms of A and B the position vector of the foot of the perpendicular from O to the line AB. So this is AB, so that means drop the foot of the perpendicular, so this is the foot of the perpendicular. We're supposed to find this point F according to the question, position vector, so we are looking at OF. Alright, so in this question we don't see any column vectors, so all the vectors are in terms of A and B. Yeah. Alright, so same idea again. In order for us to find the point F, right, so we can actually write down the position vector of F by using the equation of the line AB. Alright, so we need to form the equation of the line AB first. Alright, so to form the equation of the line AB, by now most of us will know that for equation of line we need a point. Alright, we need a point on the line. Okay, so a point on the line, in this case I use the point A. I mean, you can also use the point B if you wish. Okay, so but in this working I'm using the point A, so we take the position vector of A, the point A, which is A itself. Then we need a direction, so in this case we use the direction AB. If you want to use BA also, it's fine. Alright, so in this case I use AB. The vector AB is actually B minus A. Okay, so since F is on the line AB, right, so we can actually use this equation of the line AB, alright, to represent the position vector of the point F for some value of lambda. Alright, so we will write this. Okay, for some values of lambda. Okay, so I think yeah. Alright, so now our objective is to find the position vector of the foot of perpendicular. That means this point F lah. Alright, so in this particular representation of the position vector of the point F, we have A plus lambda times B minus A. So this lambda is not known. Alright, so once one unique value of lambda will describe this particular point F such that OF is perpendicular to this line L. So we are very interested now to find what is lambda. Okay, so again, as per normal, alright, we need to do a dot product of OF with the direction of AB, because they are perpendicular, then we will be able to get lambda. Right, so when we do that, okay, so we have this. Alright, so OF dot AB is equals to 0. Okay, that's a concept that we apply because they are perpendicular. So OF is given as this, so we dot with the direction of AB. So the thing to do now is to expand term by term. Okay, so we do it slowly, expand term by term. Alright, so we have this. Okay, so based on here, our objective, remember that we want to find lambda. Alright, so this is a vector, B minus A is a vector, so dot product, this whole thing is a scalar. B minus A is a vector, B minus A is a vector, but when we do a dot product between two vectors, the whole thing over here is a scalar. So therefore, we can actually make lambda the subject by taking this divide by this. Because this is a scalar, we can divide by that number. Okay, so simplifying, we can get lambda as this. Okay, alright, so lambda is already known in terms of A and B, not that simplified yet. Alright, so we would like to simplify this so that when things can be simplified, we should simplify. Okay, so now we want to simplify this, so we're going to do it step by step. So we're going to multiply term by term. So when we do that, we have this. Okay, maybe I will zoom a bit over. Okay, like that. Right, so when I multiply the vectors term by term, I have these components, all this. Now, A dot B happen to be 0 in this case. Why? Because we know that the vector A and the vector B are perpendicular. So once we do a dot product between them, we should get the result of scalar 0. Okay, so this thing is 0. Now A dot A, by now most of us know that is a magnitude of A squared. Okay, so the one in the denominator, similarly, B dot B will give you magnitude B squared, A dot A will give you magnitude A squared, then this one is a 0. Alright, so this whole lot can be simplified to this. Okay, so this is our lambda. Alright, so based on this newfound value of lambda, alright, we can actually take this whole thing and then put inside here to represent the position vector of the point F. Okay, so by doing that, alright, so therefore we can conclude that F is this. Okay, alright, so that's done and we have answered the question. We have found the position vector of the point F after finding what is lambda. Alright, after finding what is lambda over here. Alright, so the position vector of the point F is basically you take this value of lambda, you are going to put inside here. Okay. Alright, so that's it for this question. Alright, so that is the end of the lecture part of vectors 2. Alright, so in a couple of weeks we are going to finish off vectors with the third segment of vectors. We call it vectors 3, where we will look into planes. Okay, not aeroplanes, okay, planes, Planes. Alright, so I'll see you next time.
We've already been exposed to points and lines. Now let's think about planes. And you can view planes as really a flat surface that exists in 3 dimensions that goes off in every direction. So for example, if I have a flat surface like this, and it's not curved, and it just keeps going on and on and on in every direction. Now the question is, how do you specify a plane? Well, you might say, well, let's think about it a little bit. Could I specify a plane with one point right over here? Let's call that point A. Would that alone be able to specify a plane? Well, there's an infinite number of planes that could go through that point. I could have a plane that goes like this, where that point A sits on that plane. I could have a plane like that. Or I could have a plane like this. I could have a plane like this, where point A sits on it as well. So I could have a plane like that, and I could just keep rotating around A. So one point by itself does not seem to be sufficient to define a plane. Well, what about 2 points? Let's say I had a point B right over here. Well, notice the way I drew this, point A and B, they would define a line. For example, they would define this line right over here. So they could define this line right over here. But both of these points, and in fact this entire line, exists on both of these planes that I just drew. And I could keep rotating these planes. I could have a plane that looks like this. I could have a plane that looks like this, that both of these points actually sit on. I'm essentially just rotating around this line that is defined by both of these points. So 2 points does not seem to be sufficient. Let's try 3. So there's no way that I could put, well, let's be careful here. So I could put a third point right over here, point C. And C sits on that line, and C sits on all of these planes. So it doesn't seem like just a random third point is sufficient to pick out any one of these planes. But what if we make the constraint that the 3 points are not all on the same line? Obviously, 2 points will always define a line, but what if the 3 points are not collinear? So instead of picking C as a point, is there any way to pick a point D that is not on this line, that is on more than one of these planes? Well, no. If I say, well, let's say point D, let's say point D is right over here, so it sits on this plane right over here, one of the first ones that I drew, so point D sits on that plane. Between point D, A, and B, there's only one plane that all 3 of those points sit on. So a plane is defined by 3 non-collinear points. So D, A, and B, you see, do not sit on the same line. A and B can sit on the same line. D and A can sit on the same line. D and B can sit on the same line. But A, B, and D does not sit on. They are non-collinear. So for example, right over here in this diagram, we have a plane. This plane is labeled S. But another way that we can specify plane S is we could say plane, and we just have to find 3 non-collinear points on that plane. So we could call this plane AJB, AJB. We could call it plane JBW, plane JBW. We could call it plane, and I could keep going, plane WJA, WJA. But I could not specify this plane uniquely by saying, so I could not say plane AB, BW. And the reason why I can't do this is because A, B, W are all on the same line, and this line sits on an infinite number of planes. I could keep rotating around the line just as we did over here. It does not specify only one plane.